Hi everyone, I am here to give you a small presentation on our project Realistic Train Simulator that we designed for Texas Instruments India and Lock Design Contest 2014. During the presentation, I will tell you about the various factors that motivated us, the overall design of our project, and the hardware and software implementation of the design. We discovered that one of the major reasons for accidents on railway tracks is error on the part of driver. This can be corrected to some extent by improving the training facilities. In this regard, we found that there is a stark contrast to the training facilities available in India as compared to foreign countries. Simulators which form a major part of training are very few in number in our country. The major reasons being no indigenous manufacturer and very high cost. Our project aims at providing training to loco pilots at a rudimentary level, making efficient use of strapped and shunt locos. Train simulators which are currently available in India are imported mainly from SIDAC, which is an Australian firm, or from Quest, which is a French company. Consequently, they are very expensive. Cheaper alternatives are also available, but they don't give a realistic feel. They have limited functionality and their control panel differs from the actual locomotive control stand that are used by the driver. However, they are still expensive than our simulator. Ours is an indigenous model making use of shunt locomotive parts, which drastically reduces the cost of the simulator. Increased viability of our project is due to the fact that it is applicable to both ALCO and GM family of locomotives, which form a large part of diesel locomotives used in India. Moreover, we have used readily available off-the-shelf components to design and develop various parts of the simulator. This is a snapshot from the train simulator software, which shows a locomotive cab. This resembles an actual locomotive cab that a driver uses. Here you can see the different controls. This is a throttle lever, a reverser handle, brake levers, and there are different gauges and meters that are available with the driver, which indicate the pressure gauges, and speedometer and load meter are also available. Next. This point describes the different input-output peripherals of our simulator. We take throttle, reverser, and switch inputs from the locomotive control stand and feed them through opto-isolators to the Stellaris microcontroller. For regulating brake handles, we use potentiometers and filter and scale them using filter and scale the signals using an analog front end before feeding them into the microcontroller. Here you can see that we have used low pass filter using UAF42 filter circuit to provide tactile feedback to the locomotive driver. Next. Here you can see we are using Stellaris 7PS9092 microcontroller board for taking inputs from the locomotive control stand and feeding them to the PCB. The various inputs from the throttle lever and reverser handle, as well as the inputs from push buttons, are fed to the microcontroller analog channels through opto-isolators to protect them from damage. Brake handles A9 and SA9 are interfaced using a potentiometer and filtered using a front-end circuit before feeding them to the microcontroller networks. For driving the different gauges and meters, the data obtained from the simulator software is processed using a TIVA C-series launchpad, which sends the signal to drive the speedometer and load meter using PWM input. And for the different pressure gauges, the brake cylinder, brake pressure, and main reservoir pressure gauge, we are using servo motors to drive them. Next. Here is the overall system level block diagram of our project. Here you can see we have used a 24 volt or 12 volt power supply for driving the circuit. The different inputs from the control stand are indicated over here. We take the inputs from throttle lever through an isolation circuit before feeding them to the microcontroller. We are using a TLP2374 based circuit for filtering and scaling the analog inputs from the potentiometer. All of this data is fed to the PC using USB. From there, from the PC data is sent to the TIVA C-series microcontroller for driving meters and gauges. We are using a separate isolated power supply for servo motors to prevent loading on the USB outputs of the PC. We are also using an audio filter circuit, which is a UAF42 filter circuit for driving tactile sensors for vibration actuation of the loco pilot steer. Next. Now we come to the actual hardware implementation of our design. In the picture above, you can see a Stellaris. You can see the Stellaris board is over there, and below it there are these opto isolators and this power isolation circuit for to protect the board pins from damage. Below the board there is this TLD2374 filter circuit, which is zoomed in this picture. This is used for filtering and scaling the inputs from the different potentiometer pins which will be connected to these two inputs. Next. In the first photo above, you can see the EVA C series board which we are using for driving the servo motors for the pressure gauges and for giving PWM output to the speedometer and the load meter. In the zooming shot over below, there is a resistance circuit which we have designed for powering the different LEDs of the pressure gauge. Next. This is a snap of the UAF42 based low pass filter circuit which we are using to give tactile feedback to the driver's seat. In the picture below, you can see there is an isolated DC-DC converter for powering the servo motors. We have implemented this to protect loading on the USB ports of the motor. Next. In these two pictures, you can see the final hardware implementation of our project. This is an actual Alco 251P control stack that we are using. In this, you can see these are the controls: reverser handle, throttle lever, load meter, speedometer, pressure gauges, and brake handles. These are the hot switches, and this thing over there is an initial design of the tactile feedback transducer that we have implemented. In the picture below, you can see our project in action, and the simulator software can be seen in the LCD screen. Next. This point summarizes our final hardware design. Here you can see the different TI components that we have used. On the input part, we are using a Stellaris board for taking inputs from the control stack. TLB2374 quad op-amp is being used for filtering and scaling analog inputs from the potentiometers. We are using TIVA C series launchpad board for driving motors and gauges. UAF42 filter circuit is being used for the audio tactile feedback system. We are also using isolated DC-DC converter for powering the servo motors. Yes. This table summarizes the controls that we have interfaced with an Alco control stack. These include throttle and reverser handle, hot, saddle, and brakes on the input part, and meters and gauges, load meter, speedometer, and pressure gauges on the output. We can extend it to other diesel and electric locomotives with minor modifications in their design. Next. Here are actual performance results of UAF42 filter grabbed on a DSO in the lab for 100 Hz and 120 Hz. There is virtually no output above 1 kHz. The tactile vibration feedback mechanism adds a lot of realism to our train simulator project. Next. This point shows the different weather conditions that can be simulated in our project. Here you can see this shows a locomotive cab simulation for rainy weather. Here you can see snow. These weather conditions can be used to train the driver how to use the sampler and other features. For instance, on a foggy day or other scenarios can be created using the simulation software. Next. Concluding the presentation, I would like to make a few points. Through our project, we have been able to show that it is possible to implement a low cost but still realistic train simulator. Our project can be used, has the features of easy accessibility, and it can be used for initial locomotive familiarization and rudimentary training. We find that it is suitable for installation at different crew resting points and crew lobbies across the Indian railway network. There are some limitations. It is an imitation only. A simulation is after all an imitation and not 100% clear. And the cost effectiveness of our project depends on the availability of scrap locomotive control styles. Talking about the further prospects of extension, we can extend it to the heritage steam locomotives that are no longer being used. We can implement hydraulic or pneumatic feedback actuation to give a more realistic feel to the driver. Locomotive modeling specifically for engine conditions and engine scenarios can be implemented, and we can use protective devices and extra speedometers to enhance the viability of the project. Next. At the end, I would make a mention of these references. First is www.uktrainsim.com, which is a universal resource for train simulator development community. From the forum, we learned about editing UMA scripts for modification of different parameters of the train simulator, and we also found useful information on extracting data and variables from the train simulator software. These are two resources that we used to learn about low-pass filter circuit design for implementing the tactile feedback vibration system, which forms a very important part of the project.